and currently I also work in the astronomy department. So I did research in distributed computing, getting lots of computers to work together on things, and that led me to this area of volunteer computing. The basic idea is that if you look at the computing power in the world, there's some of it in organizational settings like clusters in departments and commercial clouds, supercomputer centers. And then there's a lot more computing power in consumer products like computers, video game consoles, smartphones these days actually have a lot of computing power. And all these things are now on the internet. So if you're interested in doing scientific computing, the type of computational science that needs basically as much computing power as it can get, it's sort of logical to look at the consumer side. With organizational resources, you have to pay for them. With consumer resources, it turns out that if you ask people nicely and get them interested in the science that you're doing, you can get them to volunteer their resources. So, SETIhome was one of the earlier volunteer computing projects. It launched in 1999. It's been based at the Space Sciences Lab, and it's run continuously since then. It gets extended in various ways using new sources of data and better algorithms and so forth. There were several other volunteer computing projects that started about the same time, like Folding at Home. But SETI was kind of a logical choice, first of all because its computational requirements matched volunteer resources well. We had this data that we needed to do signal processing on. We could break it up into a lot of pieces, run on a lot of different computers. And secondly, SETI is a goal, a scientific goal that I think interests a lot of people. As well it should. The basic idea is to see if there's life outside of Earth, and in particular if there's intelligent life. And if there is, to see if we can somehow get hold of its encyclopedia, its collected knowledge in every area you can think of. As a musician, I'm really interested in what sort of music aliens have, or if they have anything analogous to music. It would be great to learn about their math and see how it matches up with ours, see if they've learned anything about government that we haven't figured out. There's a bunch of different ways to do SETI, to look for life outside Earth. The first approach that people thought of was radio SETI, and that's actually what SETIhome is, a radio SETI project. The idea is to listen for signals in the radio spectrum. Partly that's because we produce leakage. Our TV stations and radio and radar radiate out into space, and we're hoping that aliens might have something like that. Or they might intentionally be beaming radio signals to us. There's a bunch of other approaches. You can look for laser flashes. Aliens might communicate between different planets using laser beams, and they could, flash out into space. You can look for more primitive life by building a telescope that can image planets and looking at the spectrum of their atmosphere and seeing if there's oxygen there. A lot of people think that we should really be looking for physical probes in our solar system that were sent here by aliens that would have the advantage that the probe could arrive here and then stay here for billions of years, where these other approaches, radio and optical, require that the aliens actually be transmitting, and because time is very large, that makes things somewhat less likely. Another approach that I think is really cool is to look at the light curves from stars. People have been doing this to look for planets, where a planetary disk passes in front of a star and its luminosity function goes down and comes back up again. But if aliens were to make a non-circular object, like let's say a big triangle, and orbit it, we would see a luminosity function with linear parts, and then we'd notice something is interesting there, and we could go look at it. And people are in fact looking at that using data from the For some reason, people think that SETI is an organization. It's not. There is no overarching SETI umbrella project. There's a bunch of separate SETI projects at various institutions in many different countries. And Berkeley happens to be kind of the epicenter of SETI research. And in the past couple of years, we've started a thing called the Berkeley SETI Research Center, which is part of the astronomy department. And a number of different projects are going on in the context of this. Many of them are radio SETI projects, and people from the BSRC who are very good at building digital instruments to record data and do signal processing in real time are working with all of the big radio observatories on Earth. Arecibo's the one we've been using for a while. It's in Puerto Rico. Green Bank is in West Virginia. It's sort of a different instrument. It's aimable and it has a much higher frequency response. The Chinese are building a version of Arecibo that will be like 10 times as big. Let me talk a little bit about radio SETI. The one nice thing about radio waves is that they go through the dust that you find in interstellar space. So we have a chance of hearing radio waves from various parts of the Milky Way galaxy, whereas we couldn't necessarily see visible light. Radio telescopes, like the ones I showed in the last slide, are basically kind of like single pixel cameras. They focus, they get an image from kind of a Gaussian-shaped disk whose size depends on the aperture of the telescope. You can also use radio telescopes as transmitters. So instead of having an omnidirectional radio signal, if you want to, you could focus radio power at a single point. And if somehow the aliens knew where we were, they could direct a radio beacon towards us that we'd be much more likely to see. Of course, everything in the universe that's warm gives off radio waves. So radio SETI looks for kinds of signals that aren't known to occur in nature. The most basic type is a narrowband signal where all the energy is concentrated at a single frequency or a very small frequency range. The tool for doing the signal processing is something called the Fourier transform, which you find everywhere, where you take a time domain signal and the fast Fourier transform converts it into power as a function of frequency. And if you see a very narrow spike there, it's likely to, well, it won't be black body radiation. It'll probably be man-made interference, or it possibly could be an alien signal. Radio SETI has a large set of challenges. One is that we don't know, we're just guessing about what we should look for. We don't know if aliens are sending narrowband signals. They could also be sending pulse signals that have bigger bandwidth and a pulse on and off. They may be using spread spectrum communication like cell phones do that we potentially could see if we knew how to look for it. So also the question of what frequency range? Yeah.
I was curious, I thought you said anything warm gives off radio waves.
Yeah.
Can you say a few words about that?
Well, it's black body radiation, that's as much as I understand.
Okay.
There's the issue of whether we should be looking at specific targets like stars, or maybe stars that are known to have planets. In contrast, we're doing a sky survey where we look at the whole sky and could potentially see things that are not near stars. The problem is compounded by the fact that we humans produce huge amounts of radio waves that bounce off the upper atmosphere and leak into telescopes. So the signal you get in a telescope looking at space actually has a lot of stuff coming from Earth, and we have to figure out how to cancel that out. In addition, if we're looking for a narrowband signal at a particular frequency, what we would actually detect, because of the acceleration of the Earth and its orbit and rotation, and also the sender's reference frame, would be a drifting signal because of the changing Doppler shift. So anyway, so SETIhome is a radio SETI project We use data from the Arecibo telescope. It's a sky survey. We don't control the telescope. Other people use the telescope, and we just get the data from wherever it happens to be pointing, so we end up with a sky survey. We use volunteer computing as a front end. So we get this data, chop it up into pieces, actually about 2 minutes duration and 10 kilohertz bandwidth. Send it out to computers, and this application that we've developed uses all sorts of FFT lengths so it can find both narrow bandwidth and narrow time pulses. It looks for a variety of different signal types, and it looks over a whole range of these drift rates because of the changing Doppler shift. The second part of SETIhome, which is actually what I'm working on these days, is a back end where we take all these signals that have accumulated. We've been doing this for 15 years, and we have about 10 billion signals. And the back end, first of all, we have to figure out where the RFI is. The man-made interference tends to be in little frequency ranges. Those change over time, and we have to sort of lop those out. And then we chop the sky up into a bunch of pixels using a system called HealPix. And for each pixel, what we do is look at all the signals we've received that are in that pixel and compute the probability that those signals would have arisen from noise. So we kind of score the pixels. We find the ones that have the most improbable contents. And then we look more carefully at those. In general, we find out that they actually are RFI2 that we didn't take into account. But at some point, we would re-observe those places in the sky and see if we still see the same thing. So let's skip over that. Shortly after we started SETIhome, I developed this software called BOINC, which is the kind of the middleware. We needed to make SETIhome more general so that we could release new versions of the application without requiring the volunteers to re-download something. So BOINC is this kind of framework where the volunteers install an application. They can sign up for different projects, and there's a lot of different projects. And then the BOINC client goes out and gets jobs to do, it runs them in the background. The server part of BOINC keeps track of jobs. It has potentially applications for a lot of different kinds of computers, you know, Mac and Windows and Android and programs that use GPUs and so on and so forth. And it figures out what the best version is to use for each job. BOINC also has to deal with some kind of rough edges of volunteer computing. When you're using these anonymous public computers, some of them fail. Some of them send you back bad answers, and there are some of them that maliciously do that. They try to get credit for computing that they didn't actually do, maybe by sending back a result from a previous job that they didn't really compute. So BOINC has mechanisms for dealing with that, as well as a bunch of features in the web so that people can look at how much computing they're doing and talk to other volunteers and so forth. In the few years that I've been working on BOINC, we've added a bunch of stuff. We added support for graphics processing units, like NVIDIA and AMD chips. These generally have somewhere between 20 and 100 times the processing power of the CPU chip in the computer. And it turns out that they're actually well suited to doing scientific computing, and language systems have been developed like OpenCL and CUDA that let scientists pretty easily get their applications to run on GPUs. We spent a bunch of time building a system so that apps can run in virtual machines. One of the problems with volunteer computing is that there are all these different kinds of computers, and the scientists have to build a version of their thing for Linux and for ARM, for all the different versions of Windows. It's a kind of a barrier of entry. Virtual machines let you kind of package up your environment of choice and ship that together with the application, and then that runs on the volunteer computer no matter what its native operating system is. We use a system called VirtualBox for that. And then about 3 years ago, we got the whole thing working on Android smartphones. Android, fortunately, is actually Linux. There's Linux under the covers. So this was not as difficult as you would think. We have to compile things for ARM, the processor architecture. And we had to build a new version of the interface that makes sense on smartphones. Current smartphone chips actually have, high-end ones have an on-chip GPU that gets on the order of 100 gigaflops, which is way more than the processor in a typical PC, and it's getting up there with the performance of PCs. So a lot of different scientists have created volunteer computing projects using BOINC, and they do a bunch of different things. Essentially, any project that does simulation of physical systems has this property that it creates lots of independent jobs. When you're studying a chaotic system, you need to find the statistics of the outcome. You need to just run a lot of jobs with perturbed initial conditions. So people use that to study the way that proteins interact, or that drug candidates interact with proteins. The Earth climate modeling of the Earth. There's a project that does that. It's quite revolutionary. Other projects like SETIhome do compute-intensive analysis of a lot of data, radio telescope data in the case of SETIhome. There's also a project called Einstein at Home, which analyzes data from gravitational wave detectors, and which hopes to find the first continuous gravitational waves. CERN uses volunteer computing currently they use it to simulate the LHC accelerator and optimize its design and to simulate collisions. So altogether there are about 50 of these projects. Currently they're getting about 10 petaflops, which is about the throughput of the largest American supercomputer. There's one in China that's a few times faster than that. There's about 500,000 computers taking part. The Android version hasn't really penetrated so much. There's maybe 50,000 of those, but I'm trying to figure out how to ramp that up. The other thing that I'm working on is trying to extend volunteer computing to serve more scientists. Like I say, there's currently these 50 or so science projects, and that's been relatively static. I had hoped that thousands of scientists would use volunteer computing. That hasn't happened because there's a big overhead in setting up one of these projects. So we're starting to work with existing high-performance computing facilities like TAC, the Supercomputer Center in Austin, to add a BOINC backend so that jobs that normally would run on clusters can kind of transparently get sent out to home computers. On the flip side, we're changing the interface so that what volunteers see is not a set of projects that they can choose from, but rather a set of scientific areas or sub-areas that they can choose to volunteer to. And then there'll be something intermediate that sort of matches up jobs to volunteers. So that's about it. I didn't get